welcome to this problem walkthrough. Today, we'll explore problem number 1420, build array where you can find the maximum exactly k comparisons. This is a fascinating problem that challenges us to construct an array under specific constraints while leveraging efficient algorithms. Let's dive in and break it down step by step. In this problem, we need to construct an array of length n where each element lies within the range of 1 to m. The challenge comes from the concept of cost. The cost of the array is determined by the number of times a new maximum value appears as we move from the start of the array to its end. For example, if the array is 2, 3, 3, 2, 5, the maximum value changes at indices 1, 2, and 5, giving a total cost of 3. Our goal is to find how many different arrays we can build such that the cost is exactly k. Since the total number of arrays can be very large, the result must be computed modulo 10⁻9 plus 7. To clarify the input and output format, we are given three integers, n, the length of the array, m, the maximum value any element in the array can take, and k, the exact cost we need for the array. The output is a single integer representing the number of valid arrays that satisfy the conditions. For example, if n equals 2, m equals 3, and k equals 1, the output is 6. This is because arrays such as 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, and 3, 3, all have a cost of 1, as the maximum value only changes once. The explanation breaks down how these arrays meet the cost requirement. Now consider another example where n equals 5, m equals 2, and k equals 3. In this case, the output is 0 because it is impossible to construct an array of length 5 using only the numbers 1 and 2 that has exactly 3 cost changes. With only 2 possible values for array elements, the maximum value can change at most once or twice, so a cost of 3 is unattainable. On the other hand, if n equals 3, m equals 4, and k equals 2, the output is 24. This is because there are many valid arrays, such as 1, 2, 2, 1, 2, 3, 1, 3, 3, and others, where the maximum value changes exactly twice as required. To summarize, the constraints of the problem ensure the solution space is manageable but still requires careful thought. The length of the array, n, is capped at 50, and the maximum value of any element, m, is at most 100. The cost, k, ranges from 0 to n. Edge cases include scenarios like k equals 0, where there are no valid arrays unless all elements are identical, or k greater than n, which is impossible since the cost cannot exceed the array length. Another edge case is when m equals 1, where all values in the array must be the same, making the cost either 1 or 0 depending on the value of k. These constraints and examples highlight the importance of exploring all valid approaches to solve the problem efficiently. To solve this problem, we start by considering a naive brute force approach. The intuition behind this method is simple: generate all possible arrays of length n where each element is within the range, 1 em. For each array, we count how many times a new maximum is encountered, which we refer to as a comparison. If this count matches the target k, we consider the array valid and increment our result. While this idea is conceptually straightforward, it quickly becomes impractical. The total number of arrays grows exponentially as m⁻n, making it computationally impossible to evaluate all possibilities for large values of n and m. For example, if n is 50 and m is 100, the number of arrays to check is astronomically large. This leads to an exponential runtime, and the approach doesn't take advantage of any overlapping subproblems. Hence, it's inefficient and unsuitable for this problem. In contrast, the optimized approach leverages dynamic programming. Here, we break the problem into smaller, manageable subproblems by defining a state representation that tracks the number of ways to construct valid arrays. Specifically, we use a state dp, I, max_so_far, comparisons, to represent the number of ways to build an array of length I with a given maximum value and a specific number of comparisons. This transition from brute force to dynamic programming marks the key step toward efficiency. Now, let's delve into the key observations that make the dynamic programming approach work. When constructing an array, each new element gives us two choices. First, we can add the element without increasing the current maximum value, which means the number of comparisons remains unchanged. Alternatively, we can introduce a new element that becomes the maximum, incrementing the number of comparisons. To model these choices, we use specific transition formulas. If the new element is less than or equal to the current maximum, it simply extends the array without changing the comparisons. This contribution is captured as dp, I1, max_so_far, comparisons. On the other hand, if the new element exceeds the current maximum, it introduces a new comparison. In this case, we sum over all possibilities of the new maximum x from max_so_far plus 1 to m, and add the contribution dp, I1 x, comparisons 1, for each valid x. The base case is simple. There's exactly one way to build an empty array, so dp 0, 0, 0 equals 1. This framework works because it avoids redundant calculations by reusing previous results and incrementally building up the solution. The time complexity of this approach, n*m*k, is vastly more efficient than brute force, and the space complexity is also manageable at n*m*k, as it only requires storing the dp table. We ultimately chose the dynamic programming approach because it offers the best balance between correctness and efficiency. The brute force method is computationally prohibitive due to its exponential growth, while the DP approach takes advantage of the problem's overlapping subproblem structure to reduce runtime significantly. Of course, there are trade-offs. The DP table requires space proportional to n*m*k, which can be substantial for very large inputs, and implementing the solution involves careful handling of state transitions to avoid errors. However, this approach is optimal within the given constraints. It directly addresses the problem's requirements and scales efficiently for typical input sizes, such as n, m, k up to 100. It avoids the combinatorial explosion of brute force and is simpler to implement than alternatives like memoized recursion, which has similar complexity but higher overhead. The key breakthrough was recognizing that the problem could be broken into manageable subproblems by defining a state with parameters for the current length, maximum value so far, and the number of comparisons. This insight allowed us to avoid generating arrays explicitly and focus instead on incremental computations. For these reasons, the DP approach is our recommended strategy for solving this problem efficiently and effectively. To tackle this problem using the brute force approach, we need to carefully follow a series of steps. First, it's crucial to understand the input parameters. You are provided with three integers, n, m, and k. Here, n represents the length of the array you need to build, m defines the range of values that each element in the array can take, specifically between 1 and m, and k is the target number of times you should encounter a new maximum value while traversing the array. Once the inputs are clear, the next step involves generating all possible arrays of length n where the values lie within the range, 1 m. This can be achieved using recursion or nested loops. For example, if n is 2 and m is 2, the possible arrays are 1, 1, 1, 2, 2, 1, and 2, 2. This step essentially lays the foundation for evaluating all potential combinations that might satisfy the problem's constraints. After generating all possible arrays, the next step is to simulate the traversal of each array. This means iterating through the array from left to right while keeping track of the current maximum value encountered so far. Each time you encounter a new maximum value, you increment a counter. For instance, consider the array 1, 3, 2, 4. As you traverse, the new maximums appear at indices 0, 1, and 3, corresponding to the values 1, 3, and 4. Once the traversal is complete, you compare the counter, which represents the number of new maximums, to the target k. If the counter matches k, you increment a global counter that keeps track of how many arrays meet this condition. Finally, when all arrays have been processed, the value of the global counter, which represents the number of valid arrays, is returned as the result. The brute force approach, while straightforward, has some important characteristics and insights to consider. First, it has exponential complexity since it generates m*n arrays, where m is the range of elements and n is the array length. This makes it computationally infeasible for larger values of n and m. A critical aspect of solving this problem is efficiently counting the number of new maximums encountered during the traversal of each array. By keeping track of the current maximum as you iterate, you can avoid unnecessary recalculations. Additionally, there are key edge cases to keep in mind. If k is greater than n, the result will always be 0, as it's impossible to encounter more maximums than the total number of elements in the array. Similarly, if m equals 1, there will always be exactly one new maximum, the first element of the array. To implement this approach, you'll rely on data structures such as arrays to store possible combinations, a counter variable to track new maximums during traversal, and a global counter to tally valid arrays. Given the exponential nature of the brute force approach, optimizations can significantly reduce the computational overhead. One effective strategy is pruning. While generating arrays, you can terminate further processing of an array if the number of new maximums has already exceeded k, as it will never meet the condition. Another optimization is memoization. By caching results of subproblems, such as the number of valid arrays for smaller values of n or m, you can avoid redundant calculations. Let's consider an example to illustrate these concepts. Suppose the input parameters are n equals 3, m equals 2, and k equals 2. First, you generate all possible arrays of length 3 where each element is in the range 1, 2. These arrays include 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 2, 1, 1, 2, 1, 2, 2, 2, 1, and 2, 2, 2. Next, you simulate the traversal for each array and count the new maximums. For instance, in the array 1, 2, 1, new maximums occur at indices 0 and 1, corresponding to values 1 and 2. You then check if the total count of new maximums matches the target k. After simulating the traversal for all arrays, you count the ones that meet the condition of having exactly k new maximums. For the example input, the arrays 1, 2, 1, and 1, 2, 2 are valid because they both have exactly 2 new maximums. Since there are 2 valid arrays, the result is 2. This concludes the brute force approach with its optimizations, providing a clear path to solving the problem, albeit with significant computational effort for larger inputs. By identifying valid arrays through careful traversal and leveraging techniques like pruning and memoization, the solution can be made more efficient even within the constraints of an exhaustive search. This Python implementation solves LeetCode problem number 1420, build array where you can find the maximum exactly k comparisons. Let's break it down step by step. The function number of arrays takes 3 parameters, n, length of the array, m, maximum possible value in the array, and k, number of times a new maximum value is introduced. The problem is solved using dynamic programming. #dynamic programming table. We use a 3D DP table DP, length, search underscore cost, max underscore so underscore far, where length is the current array length being considered. Search underscore cost is the number of times a new maximum value has been introduced. Max underscore so underscore far is the current maximum value in the array. ## base case. When length equals 0 and search underscore cost equals 0, the only valid array is an empty array. Therefore, dp 0, 0, 0 equals 1. ### filling the DP table. For each possible array length, 1 to n, search cost, 1 to k, and maximum value, 1 to m. 1. Case 1, extending the array with a number equals max underscore so underscore far asterisk. If we append a number less than or equal to the current max, the maximum doesn't change, and the search cost remains the same. The number of ways to do this is dp, length 1, search underscore cost, max underscore so underscore far, asterisk max underscore so underscore far, since we can choose any of the max underscore so underscore far numbers. 2. Case 2, introducing a new maximum asterisk. If we append a number greater than the current max, the new number becomes the maximum, and the search cost increases by 1. For each possible new maximum, we add dp, length 1, search underscore cost 1, new underscore max. ### result calculation. Finally, we sum up all valid arrays of length n, search cost k, and any maximum value, 1 to m. The result is returned modulo 10⁻9 plus 7. This approach efficiently handles the constraints using dynamic programming, ensuring a time complexity of approximately O, n times k times m squared, which is suitable for the problem's constraints. Here, we start by importing the necessary utilities and defining the solution class. The core method, number of arrays, takes 3 parameters, n, the length of the array, m, the range of numbers from 1 to m, and k, the exact number of comparisons to find the maximum. We define a constant mod to handle large numbers as the result must be computed modulo 1 billion in 7. Next, we declare a three-dimensional dynamic programming array, DP, where DP, length, search cost, max so far, represents the number of valid arrays for a given length, search cost, and maximum value so far. The base case is initialized such that DP 0, 0, 0 is 1, representing one valid empty array when the length and search cost are 0. The nested loops iterate over possible lengths, search costs, and maximum values. For each configuration, we handle two cases, extending the array with a number less than or equal to the current maximum, and introducing a new maximum. In the first case, we multiply the previous state by max so far because any of the numbers up to max so far can be added. In the second case, we iterate over potential new maximum values smaller than the current max so far, updating the DP table accordingly. Both cases ensure we stay within the mod constraint to avoid overflow. Finally, we compute the result by summing up all valid arrays of length n, with a search cost of k, across all possible maximum values. To do this, we iterate over max so far from 1 to m, adding dp, n, k, max so far, to the result, and applying the modulo operation to ensure it stays within the specified limit. Once the summation is complete, we return the result, which represents the total number of arrays that satisfy the given constraints. This implementation efficiently handles the problem's requirements using dynamic programming, ensuring that we account for all possible scenarios while keeping the calculations optimized. We begin with the setup for the first example, where we need to build arrays of length 2 using integers between 1 and 3, such that the search cost, or the number of times a new maximum is introduced, is exactly 1. To tackle this, we use dynamic programming and define a three-dimensional array, dp, length, search underscore cost, max underscore so underscore far, to track the number of valid arrays. Initially, the entire dp array is filled with zeros, and the base case is defined as dp 0, 0, 0 equals 1, which represents an empty array with no cost. Now, we iterate over the possible lengths, search costs, and maximum values. For length equals 1 and search underscore cost equals 1, a single element array introduces a new maximum. For each possible maximum value, we set dp 1, 1, 1 equals 1 for the array 1, dp 1, 1, 2 equals 1 for 2, and dp 1, 1, 3 equals 1 for 3. This initializes all valid arrays of length 1 with a search cost of 1. Next, for length equals 2, we calculate the number of arrays based on the previous values. For search underscore cost equals 1 and max underscore so underscore far equals 1, we can extend 1 only with numbers less than or equal to 1, resulting in 1, 1. This gives dp 2, 1, 1 equals dp 1, 1, 1 asterisk 1 equals 1. For max underscore so underscore far equals 2, we extend 2 with numbers less than or equal to 2, resulting in arrays like 2, 1, and 2, 2. Here, dp 2, 1, 2 equals dp 1, 1, 2 asterisk 2 equals 2. Similarly, for max underscore so underscore far equals 3, we extend 3 with numbers less than or equal to 3, producing dp 2, 1, 3 equals dp 1, 1, 3 asterisk 3 equals 3. Finally, we sum all dp 2, 1 max underscore so underscore far values for max underscore so underscore far equals 1, 2, 3 to get the total number of valid arrays of length 2 with a search cost of 1. The result is 1 plus 2 plus 3 equals 6. Therefore, the output for this example is 6. Now, let's explore the second example, where we need to create arrays of length 3 using integers between 1 and 2, with a search cost of exactly 2. Similar to before, the base case is dp 0, 0, 0 equals 1. For length equals 1 and search underscore cost equals 1, we initialize dp 1, 1, 1 equals 1 for 1, and dp 1, 1, 2 equals 1 for 2. For length equals 2 and search underscore cost equals 1, we extend 1 with numbers less than or equal to 1, resulting in 1, 1, and dp 2, 1, 1 equals dp 1, 1, 1 asterisk 1 equals 1. Similarly, for max underscore so underscore far equals 2, extending 2 with numbers less than or equal to 2 gives dp 2, 1, 2 equals dp 1, 1, 2 asterisk 2 equals 2. When search_cost equals 2, we introduce a new maximum by extending 1 to 1, 2, resulting in dp 2, 2, 2 equals dp 1, 1, 1 equals 1. These values set the stage for the next step when length equals 3. For length equals 3 and search_cost equals 2, we extend arrays of length 2 that already have a search cost of 2. Specifically, we take 1, 2, and extend it with numbers less than or equal to 2. This results in dp 3, 2, 2 equals dp 2, 2, 2, asterisk 2 equals 2. To calculate the final result, we sum all dp 3, 2 max_so_far values for max_so_far equals 1, 2. Since dp 3, 2, 1 is 0 and dp 3, 2, 2 is 2, the total is 0 plus 2 equals 2. Thus, the output for this example is 2. In the third example, we focus on arrays of length 2 using integers between 1 and 2, with a search cost of exactly 2. As always, the base case is dp 0, 0, 0 equals 1. For length equals 1 and search_cost equals 1, we initialize dp 1, 1, 1 equals 1, 4, 1, and dp 1, 1, 2 equals 1, 4, 2. For length equals 2 and search_cost equals 2, we need to introduce a new maximum. This can be achieved by extending 1 to 1, 2, resulting in dp 2, 2, 2 equals dp 1, 1, 1 equals 1. Since no other configurations meet the criteria for search_cost equals 2, we proceed to the final calculation. To determine the total number of valid arrays for this example, we sum all dp 2, 2 max_so_far values for max_so_far equals 1, 2. Here, dp 2, 2, 1 is 0, and dp 2, 2, 2 is 1. Therefore, the total is 0 plus 1 equals 1. This means the output for this example is 1. With this, the solution walkthrough for the problem is complete, and we've demonstrated how dynamic programming can be used to solve it efficiently. To analyze the time complexity of our solution, we start by observing the nested loops and their contributions. First, the outer loop iterates over the length of the array, from 1 to n, which means it runs O, n, times. Next, the second loop tracks the search cost, iterating from 1 to k. This adds O, k, iterations for every value of length. The third loop handles the maximum value encountered so far, iterating from 1 to m. This means it contributes O, m, iterations for every combination of length and search_cost. Finally, within the innermost part of the loop, we have a fourth loop that considers introducing a new maximum value. This loop iterates over all potential new maximums, which, in the worst case, can go up to max_so_far and take O, m, iterations. By combining these, the innermost operation adds O, m, additional work, leading to significant computational effort as we iterate through the loops. When we combine the contributions from all nested loops, we can calculate the total time complexity. The outer loop runs O, n, times, the second loop adds O, k, the third loop contributes O, m, and the innermost operation adds another O, m. Multiplying these factors together gives us an overall time complexity of O, n times k times m squared. This quadratic dependence on m highlights the computational cost of handling large values for the range of potential numbers in the array. While the time complexity is significantly better than a brute force approach, it still reflects the challenges of solving this problem efficiently for large inputs. Now, let's look at the space complexity, which is determined by the size of the dynamic programming table, or DP. This table is a 3D list with dimensions n plus 1, k plus 1, m plus 1. Each of these dimensions corresponds to the length of the array, the search cost, and the maximum value so far, respectively. Since all dimensions are indexed from 0 to their respective maximum values, the total number of elements in the DP table is n plus 1 asterisk, k plus 1 asterisk, m plus 1. Additionally, each element in the table stores an integer, which takes constant O1 space. Therefore, the total space complexity is proportional to the number of elements in the table, leading to an overall space complexity of O, n asterisk k asterisk m asterisk asterisk. This space requirement is significant but necessary to store intermediate results and optimize the computation. To better understand the efficiency of the optimized solution, let's compare it to a brute force approach. In a naive solution, we would generate all possible arrays of length n with values between 1 and m. For each array, we would calculate the search cost and filter those with exactly k comparisons. The total number of possible arrays is m⁻n, and calculating the search cost for each array takes n operations. This results in a time complexity of m to the power of n*n** for brute force. The space complexity of this approach is n, as we only need to store a single array during generation. In contrast, the optimized dynamic programming solution avoids generating all arrays explicitly by leveraging previously computed results. This reduces the time complexity to n times k times m squared, a dramatic improvement, particularly for large values of m. However, the trade-off is an increase in space complexity to n*k*m** due to the DP table. Finally, let's evaluate the performance of the optimized approach across different scenarios. The time complexity remains n times k times m squared, in all cases best, average, and worst, because the nested loops iterate over fixed ranges determined by n, k, and m, regardless of the specific input values. Similarly, the space complexity is consistently n*k*m*, as the size of the DP table depends only on the input dimensions. To confirm this time complexity mathematically, we multiply the contributions from the outermost loop, which runs n times, the second loop running k times, the third loop running m times, and the innermost operation contributing another m. This gives n*k*m*, which simplifies to n times k times m squared. Meanwhile, the space complexity is determined by the DP table, with n plus 1 k plus 1 m plus 1 elements, simplifying to n*k*m*. This analysis underscores how dynamic programming achieves significant efficiency gains compared to brute force, especially for large-scale inputs. In this section, let's address some common mistakes that can arise when solving this type of problem. First, overlooking constraints or edge cases is a frequent issue. For example, if the values for n or m are very small or very large, brute force solutions might seem appealing but can easily time out due to their inefficiency. It's crucial to analyze the constraints carefully and test edge cases, such as n equals 1 m equals 1, or the maximum allowed values, to ensure your solution behaves as expected. Another common challenge is failing to optimize for repeated subproblems. Many problems, including this one, involve overlapping calculations that can be handled more efficiently using dynamic programming or memoization. Recomputing results for the same inputs wastes valuable time. Additionally, it's important to consider how the size of the problem affects your solution's performance. While a brute force approach might seem correct, it could fail for large inputs due to exponential growth. For instance, generating all possible arrays of length n, where each element is chosen from 1 results in m⁻n combinations, which quickly becomes unmanageable. Lastly, there's the risk of confusing similar problems or approaches. Some problems may ask you to count solutions, while others require generating them explicitly. Take the time to carefully identify what the problem is asking for and tailor your solution accordingly. Now, let's continue by discussing a few more common pitfalls and some key insights that are particularly useful in an interview context. Using incorrect base cases in recursion is another area where mistakes often happen. If your base cases or termination conditions are not well defined, your recursive solution can fail or produce incorrect results. It's always a good idea to double-check that your recursion handles edge cases properly. From an interview perspective, understanding the trade-offs between recursive and iterative approaches is essential. Recursive solutions can be more intuitive and easier to write, but they come with the risk of stack overflow for large inputs, while iterative solutions can mitigate this risk by eliminating recursion. Additionally, space complexity is often a concern in dynamic programming problems. You can optimize for space by reusing a small subset of previously computed results instead of storing everything. Beyond technical considerations, clear communication is key during interviews. Make sure to explain your thought process, especially how you plan to handle edge cases and improve the performance of your solution. Finally, for particularly complex problems, breaking them down into simpler subproblems can be incredibly helpful. For example, solving a version of the problem with smaller constraints can help you build intuition and uncover patterns that can be applied to the full problem. Next, let's explore related problems and alternative approaches that can help you build a deeper understanding of this topic. Some related problems worth studying include LeetCode 78, which focuses on generating subsets, LeetCode 39, which explores combination sums, LeetCode 46, which deals with permutations, and LeetCode 377, another variation of combination sums with a unique twist. These problems share similar elements, such as generating or counting specific combinations, and can provide valuable practice for honing your skills. When it comes to alternative approaches, backtracking is a powerful technique to consider. It systematically explores all possibilities while pruning invalid paths early, which makes it more efficient than a brute force search. However, backtracking can still be slow for large inputs, so its trade-offs should be evaluated carefully. On the other hand, dynamic programming is often much faster for problems with overlapping subproblems. By storing intermediate results and reusing them, dynamic programming can significantly reduce computation time. That said, it can require a considerable amount of memory for large inputs, so be mindful of its space complexity as well. Finally, let's cover two more approaches that you may find useful when solving this type of problem. Memoization is closely related to dynamic programming but is typically applied in a recursive context. It avoids redundant calculations by storing the results of expensive function calls and reusing them when the same inputs occur again. While this can dramatically improve performance, it does add some overhead for maintaining the storage of intermediate results. Another approach to consider is iterative generation, which eliminates recursion entirely. This method can be particularly useful for avoiding stack overflow issues in problems with large input sizes. However, iterative solutions can sometimes feel less intuitive, especially for problems that naturally lend themselves to recursive thinking. Each of these techniques has its own strengths and weaknesses, and the best choice depends on the specific constraints and requirements of the problem you're tackling. Great job following along. To summarize, we tackled problem number 1420 by breaking it into manageable steps, starting with brute force and optimizing toward an efficient solution. Remember to practice similar problems to strengthen your skills. Thanks for watching, and be sure to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!